here. So we'll be having regular sessions from now, either in the evening or morning, depending upon how you guys are free. So you can finish it as well. Alright, so yesterday we were discussing about drag. That's where we stopped discussing two types of drag. Yes, Anuj, what are the two main type of drags that we have on the aircraft?
Sir, parasitic drag and this one. Induced drag.
That's right. So we have parasitic drag and we have induced drag. So by induced drag we mean it is a lift induced drag, right? And we saw yesterday how parasitic drag, so parasitic drag itself it's composed of the skin friction drag, the form or the pressure drag, and we have the interference drag, right? And the parasitic drag is, if I write parasitic drag as the coefficient drag, it's the drag P. That is what is the relationship of parasitic drag with velocity? So what happens as speed increases to parasitic drag? So from the basic drag equation, which is drag is equal to, drag is a force which is equal to the product of coefficient of drag times the dynamic pressure times wing surface area. So having this equation in mind, you know that this dynamic pressure is half times density times square of the true airspeed, where the V over here. What is this V? This V is the TAS, and what is this indicative of? This is indicative of the indicated airspeed, right? So with this equation in mind, when you increase the velocity, what happens to your parasitic drag? It increases with the square of velocity, and on the basis of that, in the last class we saw a graph that we drew between parasitic drag and the speed. How is the graph? It increases exponentially, not linearly, because it is proportional to square of V, and therefore it increases exponentially. So out of the graph and the equation, what you have to understand is lower the speed, lower is the parasitic drag. Higher the speed, higher is the parasitic drag. Just think about opening an umbrella when you walk and when you are on a bike. So at lower speeds with the umbrella, what you experience is the parasitic drag. You experience lower parasitic drag when you walk than when you fly, when you travel on a bike at a higher velocity. You open the same umbrella, you'll have so much of drag that you fall back. Right? You know how with the increase in wind, the wind is going to catch the umbrella and you find that resistance behind, which is what is called as drag. Right? That is exactly what a parasitic drag is. So if you are confused with what or how does a parasitic drag look like, it is just like the same resistance which you get on an umbrella when you have a wind or when you actually open it while you travel. Alright? Yes. Now we also spoke about lift induced drag. One more thing, we also spoke about how to reduce parasitic drag. It's mainly by cleaning the surface, making it sure it's free of ice, dust, dirt, etc. Pre-flight thing. And we can reduce the skin friction or form drag by streamlining the surface. That is like more like a manufacturing point of view. And you can reduce the interference drag by smoothing the surfaces, by making it more curved, as in I showed you a model yesterday. If you remember, you can see how in this particular aircraft the wing is kind of curved here and not very abrupt. It's much more evident at the tail here. You can see how it's curved rather than not very abrupt, right? So this will help reduce the interference drag. So that is how we try to reduce the parasitic drag. Now you see we also saw lift induced drag here. And so how is lift induced drag produced? We spoke about three different things yesterday. One is the leaking of the air from underneath the wing, high pressure underneath the wing to low pressure above the wing. What does it produce?
Pressure difference.
Yeah, so what does the pressure difference produce? It produces wingtip vortices from under the wing all the way up, right? And on the right wing, I told you it's more like anti-clockwise. So from looking from the rear, from the back, you can see right wing is going to produce an anti-clockwise wingtip vortice and left wing is going to produce a clockwise wingtip vortice, right? And this wingtip vortices kind of pushes. So the wingtip vortice kind of pushes the air above the wing towards the wing root and the air below the wing towards the wingtip, right? So that is what is called as a span-wise flow. And because of the span-wise flow, as the air meets at the trailing edge, it won't be actually in line, and that produces trailing edge. Eddy. So this wingtip vortices plus span-wise flow plus trailing edge eddies that causes the lift to bend rearward. All these things which we saw yesterday. The rearward bending of the lift causes a lift to have its component in the direction of drag, which is what is called as induced drag. Right? That is the drag that is induced by the actual production of the lift itself. It is what is called as the induced drag. Right? Now we also discussed some of the factors affecting induced drag. Remember that? LID is lift induced drag. The factors affecting lift induced drag. What are the factors affecting lift induced drag?
Sir, angle of attack? No.
Second?
Angle of attack?
The pressure difference. So what is causing the drag? What is causing drag here? The lift itself is causing the drag. That's why it is called lift induced drag, right? And what produces lift? The pressure difference between the bottom part of the wing and the top part of the wing. That's why we say lift pressure difference is one of the factors affecting lift induced drag, right? So what is this pressure difference called? It's called as lift. So when you say that something is dependent on lift, you can also say that the same thing is dependent on something else also. So what is the meaning of lift induced drag is depending on pressure difference? Means lift induced drag is depending on lift because pressure difference is lift. What is the meaning of that? Higher the lift, higher the lift induced drag. So if you can say that lift induced drag depends on lift, you can also say that lift induced drag depends on something else, which is equal to lift. Yeah, so what I'm asking is, if lift induced drag is dependent on lift, you can say that it is also dependent on something else. Yeah, it depends on speed, but that's a different section from this. If something is dependent on lift, it also depends on something else. What is lift countering? Weight. Yeah, so it also depends on weight of the aircraft. Now think about it. If the aircraft is heavier, what should be more for it to be airborne? The lift required is actually higher, and if lift required is higher, the lift induced drag, the drag induced because of that, is also going to be high. Right? Look at an aircraft that is more into straight and level flying. Straight and level. Straight and level means the wings are level, right? And the aircraft is flying straight, not climbing or descending. Wings level, and then flying straight all the way, right? That is straight and level. Now, what is the relationship between lift and drag? So what is the basic force that we are trying to counter? Is the weight of the aircraft. To counter the weight of the aircraft, we produce lift, and the lift will act opposite to it. Now, actually speaking, this is not how the diagram would be, because the lift and weight will not be in line. You have a lift weight couple that is going to be formed. From which point is the lift acting? The entire lift of the wing is assumed to act from a point which is called as center of pressure, which is CP, which is on the core line. Right? Now the entire weight of the aircraft can be assumed to act from a point which is called as
center of gravity.
CG. Right? So the weight acts from CG and lift acts from CP. We have seen this earlier in navigation performance as well. You can see how this creates a nose down moment and the inherent tendency of the aircraft to drop its nose. We counter that by producing an elevator and a vertical downward force on the elevator. Remember all those things which you have studied before? That is because of this lift weight couple that is formed here. But basically we can say lift is actually countering the weight in a straight and level flight. So here the lift is equal to weight, right? So higher the weight, higher the lift, your lift induced drag is going to be higher, more. Yes, so you have a higher LID. Now think about an aircraft in a turn. The aircraft in a turn. So in a turn, so the aircraft is turning, not straight and level anymore. It's kind of turning the aircraft in a turn. Right? We will study turning as a separate session later. So what comes after this topic is we talk about straight and level first. We'll then talk about climb. We'll talk about descent, and then we'll talk about turning, stalling, all those things. So we'll talk about turn a bit later. I'm not explaining much here, but just for a brief idea, when an aircraft is in a steady turn, what is meant by steady turn?
Not landing, not descending.
That's right. No, that's a level turn. Level turn means the aircraft is not climbing, not descending. It's not a climbing turn, not descending turn. Remember, yes, we studied yesterday about that interception, and we saw how they make a very steady 90-degree climbing turn. That's a climbing turn. They are also turning at the same time they're climbing. But if a level turn, then they won't climb or descend, they simply make a turn, steady turn. You maintain 10,000 feet, you maintain 10,000 feet during the turn. Now that is what is called as a level turn. Now what's a steady turn? Think about rate 1 turn, which is 3 degrees per second. Every second you're turning by 3 degrees, that's a steady turn. Right? Now if an aircraft is in level and steady turn, so let's see the front view here. Right? And now the aircraft is turning. Can you just see this portion? Right. Is this side clear? Can you see it properly? That side?
Yes.
Right? You can see the aircraft is now turning. It's, from the front view, it's more or less making a left turn here. Right? And this is the aircraft front view. Let's draw this weight and lift again. So in a level turn, this is straight and level flight. The lift is acting perpendicular to relative airflow, and the weight is acting straight down, vertically in line with the gravity vector. And you can see that the lift is equal to weight. Now what about in a turn? Let's draw the vectors again here. What is going to happen to the lift? Lift is again going to be perpendicular to the relative airflow. So when you make a turn, the relative airflow is also coming from the turning side, not from straight anymore, because you're making a turn. If I'm making a left turn, relative airflow is going to come from a left. If I'm making a right turn, it's going to come from a right. Yes, and therefore the lift is going to be now perpendicular to relative airflow, which is going to be tilted. If the lift is like this now. What about the weight of the aircraft? Is the weight of the aircraft going to act tilted?
They will act downwards.
That's it. Just like imagine suspending a ball here. The ball is going to be just straight down, parallel to the gravity vector again. I want to look at these two diagrams here. Look at how the weight vectors are. The weight vectors are unaffected by the turn, but the lift vector has actually changed. Now what is the problem here? Now do you think that in the first figure you can see lift is actually counting the weight, you can stay airborne. Do you think that this lift is actually counting this weight? No, right? There is only a component of this lift. Now I can resolve this lift into two different components. One, you have a vertical component. You must have studied this in physics. Don't stress, you don't have to learn much, just understanding is the point. I can resolve this lift into two components here. So one is the vertical component, other is the horizontal component. Vertical component, horizontal component. Which component of lift is countering the weight here? Only the vertical component, right? You have a horizontal component now acting into the turn. Do you realize that? Too many pens in my hand. Alright, yes, let's see. Normal case, lift, and you have the weight. Now when you make a turn, the lift is now acting perpendicular to relative airflow. The weight is still acting straight down, and therefore now you have a component of a lift that is countering the weight, and another component of lift is now acting into the turn. Do you see that? This is kind of going to pull the aircraft into the turn. So this is what is more, which you experience as a centripetal force. Something is going to push the aircraft into the turn. Is this component that's acting into the turn? Does it make sense?
Yeah.
Right, so anything and everything is having tendency to actually go into the turn. Now you have the rudders in place, which actually kind of helps you balance this. And if you don't do it, remember in your navigation instruments, we have studied about slip and skid based on you give more rudder or less rudder compared to your turn. Right? So basically, our idea here is to understand that this entire lift is no more countering the weight. What is countering the weight here? Only the vertical component of lift is going to counter the weight. Now, what do you think about the value of the vertical component compared to the total lift? Is it going to be less or more? This is just a component of the entire lift. Yes, therefore it is lesser, right? So now you have only less lift available. Did the weight change? The weight is not changing, and therefore, do you think this vertical component will be able to sustain the aircraft in level flight? No. So what happens is, if you have a lift, you start turning, you don't do anything about it, it's going to descend. It's going to turn, but it's going to do a descending turn, because now the weight is countered only by a lesser vertical component of lift. It won't be able to, it's not that the aircraft will fall, it's going to make a small, very shallow descent all the way down as you turn. This is a very, very common practice when the instructors make you turn a 30-degree medium level turn. If you don't do it properly, the aircraft is going to lose altitude. And if you overdo it, the aircraft is going to climb. Right? So what we do is when we make a turn, we have a theory, in practice, when you actually fly, there's 3 B's. This is what you have to remember when you practically fly the aircraft. When you make a turn, you have to think about these 3 B's here. Yes, Hiloni, are you there?
Yes, sir.
Yeah, tell me the 3 B's, please. When you make a turn, level turn.
3B.
Yeah, when you make a turn, if I ask you to make a 30-degree turn to the left, what all things will you do? What do you do first? First you're going to bank.
You bank.
That's the first B. Right? When you bank, you should not skid or skip, and therefore you have to use your balancing system, which is your rudder. So you bank, so left bank, left rudder, right bank, right rudder, right? So you may bank left. While you bank, you have to apply your left rudder. And then, if you don't do anything about it, the vertical component of lift, which is lower than the actual lift, is going to descend the aircraft. Did you understand why the aircraft is descending in a turn? Because now the lift produced, that lift which is opposing the weight, is lesser than before. It's just the vertical component of lift alone. Therefore, to prevent that descent, what are you supposed to do? You have to give back pressure, which will prevent the aircraft from descending. Yeah, you use the elevators and it make a very slight pitch up attitude. If you overdo it, it's going to climb.
Yeah.
Right? Now what happens when you actually increase the turn from 30 degree to 60 degree? When you make the aircraft bank more, the lift is going to incline more, and therefore the vertical component is going to reduce further. Now you have to pitch up more if you don't want to descend. Now don't really get confused. As I told you, we'll draw separate diagrams for this under turning and tell you. Basically what I'm trying to tell you is the more you bank, the more you have to apply back pressure if you want a level turn. You will reach a point, especially when you go to 60 degree or maybe more than 60 to 60 degree or more than that, just by pitching up won't work. You have to even add power if you want to stay certain level. Yes, Hiloni, are you able to relate it, what I'm trying to say? When you make a turn?
Yes, yes.